Well, welcome back to Engineering 2219. We're up to week 9, and we're going to be talking about computer simulation. So I'll give you the rough outline. So we're going to talk about the objective simulation, what sort of different types there are, and then we're going to basically focus on two different kinds of simulation, Monte Carlo methods. We're going to talk about how we can use it to simulate games of roulette, as in a casino, and how to use it to numerically integrate functions. And then we're also going to talk about discrete event simulation and using it to simulate the flow of heat throughout like a block of material. So the objective of simulation is basically to simulate some process inside a virtual environment. We might be interested in learning some sort of properties about the environment, and instead of running real-world experiments, which might be like terribly expensive or dangerous or who knows what, we learn these properties instead by basically simulating a copy of the environment that we would otherwise do in the real world on a computer. And this means we can sort of like trial it a bunch of times and see what things happen under different circumstances quite easily and quite cheaply. So common uses for Monte Carlo, common uses for simulation include numerical integration, optimization of a certain problem. So you may have like a particular function you want to maximize, subject to a set of constraints. Simulation would be a good approach for that. Simulating physical phenomena, so heat flow, movement of fluids, like aerodynamics around like a wing on a plane, things like that. And estimating properties of some sort of stochastic process. When I say stochastic, I mean like random. So this could be like dice rolls or like playing lots of games of blackjack. You might want to know what strategies work well. And because it's such a noisy game due to randomness of the cards, you have to simulate many trials to sort of work out an average, on average, how well does this strategy work. Note that, at least for when we do Monte Carlo simulations, the underlying process doesn't actually need to be stochastic, it doesn't need to be random, because certainly the process of integrating a function is non-random. But nonetheless, we can still use Monte Carlo methods, and they're quite useful for this. So the main idea of simulation, let's talk about the advantages and disadvantages. So the advantages of doing simulation is obviously cost, right? It's way cheaper to simulate a virtual environment than it is compared to the real thing. The other advantage is time. Obviously, it's a lot faster, right, to simulate a virtual environment than it is compared to the real thing. Abstraction. Basically, suppose we wanted to work out a particular parameter environment, suppose we're working out like traffic flows, and we want to know like different strategies of setting up traffic lights, we can abstract away a lot of the stuff that doesn't matter. We don't actually care who's piloting the cars. In general, we can sort of simulate cars as like basically a little automaton that wants to go from place A to place B. The humans in the loop don't actually matter, right? So we can abstract away a lot of the details that don't matter and focus on just the parts that do. And obviously we have our full control of the entire environment. So if I want to like simulate different weather patterns or simulate peak traffic or off-peak traffic, these are like easily switches I could flick in a virtual environment. In a real environment, obviously if I want to simulate rain, I have to wait for it to rain. Disadvantages include that the model may not be a complete, accurate representation of reality. So you want to be careful. Sometimes you might have a model and then learn a strategy that works really well in that model, and then when you try and generalize it to the real world, it doesn't hold. So you have to be careful what you're allowed to generalize from a simulation. And sometimes simulations can work quite poorly if you're in a very high dimensional space and you've got like lots and lots of different parameters to tweak. It can be quite slow. Or if you need a great amount of accuracy, if you're trying to estimate parameters, especially with Monte Carlo, a large accuracy in like particular averages of, let's say, payouts in roulette or payouts in blackjack, to compute the like expected gain to a great accuracy can take many hundreds of thousands of trials, and that can also be computationally quite expensive. So when we do simulations, there's basically two things we need to model: space and time. The system and process obviously occurs in some space. I mean, the world I live in is three-dimensional, but you could be simulating a process in who knows how many dimensions. And they usually evolve as time continues. We might be interested only in how it changes over time, or we could also be interested in how it varies in space, or potentially both. Now, of course, the problem is when it comes to a simulation is that in the real world, space and time seem to be pretty continuous, but a computer is decidedly a non-continuous device. So we can actually simulate this, a computer will need to discretize and split into small parts. So there's two main approaches when it comes to modeling space. There's the Euclidean approach, which is our focus on locations in space, so focusing on like particular like grid cells in your world. And there's also the Lagrangian approach, which is the focus on the objects themselves. So with the Eulerian approach, if the space is inherently continuous, which it naturally tends to be, we can sort of approximate it and pretend it's just a very, very fine grid. And when you've got a fine grid of pixels that's sufficiently high resolution, that it's close enough quite often to a continuous space. You can imagine like a picture on a computer looks pretty smooth to your eye. At the end of the day, it's just a grid of discrete pixels. But given sufficiently many pixels, it can be, well, maybe not indistinguishable, but indistinguishable enough from a continuous reality. The Lagrangian approach is different. Rather than discretizing space, we really only keep track of the objects themselves. So we have a collection of objects in the space. I write down a coordinate point of where each one is, and then as time moves forward, I can then translate these objects through space. This might be a good approach for, say, modeling orbits of objects in outer space. Maybe you've got like a star and then planets that are going around the star. This would make sense to easily store as a collection of coordinates, right? Because again, we can sort of abstract away the details that don't matter. I can just pretend the star is a point mass that weighs this much at this location, and all the orbits will end up being the same. So we can sort of abstract away the details that don't matter. And this is really important when you want computational efficiency in your simulations. Okay, so that's how to model space. Modeling time, a similar approach. So the usual tactic is called time slicing. We basically take the otherwise continuous timeline and split it up into little chunks, little blocks. And each of these blocks is basically a discrete time step. And the assumption that we make is that the environment is constant. It doesn't change over a little small instantaneously, well, not instantaneous, but a little small piece of time. And at the end of each time step, the environment instantaneously changes. So basically, in each tick of the time step, the environment transitions to the next state. And the reason why this is justified is that over very, very short time periods, most environments look to be constant, right? I mean, if you step through this video frame by frame, I don't move much over a frame, but over many seconds, I do, right? So much like this video is not continuous, it's cut up into frames, we can basically simulate any continuous environment, or at least approximate any continuous environment as a collection of time steps. And the limit of the time steps get very small. It basically can be an almost perfect representation of like true continuous time. So let's talk about some examples now of using simulations. So the first one I'm going to talk about is roulette. So roulette is a gambling game where you can basically bet on a number or bet on a color, and a ball will spin around a wheel and land in one of 38 pockets with equally likely chance. So a roulette wheel has the numbers 1 to 36 on it, and they alternate red and black. And it's also got 2 additional pockets that are colored green. We'll consider for the moment just betting on a single color, let's say red. So the math indicates that this is probably not a game you'd want to play. And why is that? Well, the probability of success when I bet, like wager $1 on red, is the number of successful outcomes, which is the number of red pockets, which is 18, divided by the total number of pockets on the board, which is 38. That comes out to about 48%, which is a bit less than a half. So this game is unfair. It's biased towards the house and biased against the player, which should be no surprise. Casinos are in the business of making money, after all. So we can compute the expected value or the average return per bet. And so what's that? It's basically, on average, when you play many rounds of this game, how much money do I stand to win or lose per spin on average? And so we can compute that as basically the product of how likely I am to win times the payout I get if I win, plus how likely am I to lose times the payout, in this case it would be negative payout because I lose money, when I lose. So the likelihood of me winning was 9/19 times, well, if I wager $1, and I get red, that means I win $1, so my bankroll increases by $1, plus the probability of a loss, which is 10/19 times the payout to me if I lose, and the payout to me is negative $1 because I have to give the casino $1, and we multiply that all out, and we end up with minus 1/19, or approximately minus 5 cents. That is if we assume we're wagering $1 each time. So what does that mean? It means, on average, I stand to lose 5 cents a spin. Well, I mean, that doesn't make sense. I can only lose or gain $1, so what does it mean to, what are we talking about, 5 cents here? Well, basically, in the limit of playing many, many spins of this, if I were to play this, let's say, 1,000 times, then after 1,000 spins, it's the most likely outcome is that I will have lost 1,000 times 0.05, which would lead to an expected loss of $50 over 1,000 spins. Not great, probably shouldn't play this game. So that's what the math tells us. Could we actually simulate this and see what it looks like in practice? And of course we can. We can easily write a Python script that basically pretends to be a roulette wheel. We'll start with a bankroll of $100, and we bet $1 spin, always on red, and then we can watch the gambler's total bankroll shift up and down during the course of a run. So let's have a look at the code here. So betting run is basically recording my bankroll as a function of time. Starts at 100. For I and range trials, where trials is some variable that dictates how many spins the roulette wheel we're going to simulate. P, we generate a random number between 0 and 1. If P is below the bias, in this case the bias of the wheel was 9/19, or about 48%, that counts as a win, in which case my bankroll increases by whatever I wagered. In this case we're wagering $1. Else, the bankroll decreases by whatever my wager was. Then we record my bankroll in the list betting run and basically run it again. So we can run a few of these. So here I've ran 5 trials of this roulette simulation. And in some of the trials I get a profit. So you can see in the orange one and in the green trial for a bit of time, I managed to make a profit. Whereas in the purple and the blue and the red trials, I made a loss. And these are all independent trials. So each trial started from the same position at $100. And we just spin the wheel 50 times, betting $1 each time on red. So you can see for only 50 spins, it's quite noisy. The data's sort of all over the place, right? Sometimes we win, sometimes we lose, and sometimes the gambler actually does make a profit in this game. But eventually, in the long term, the house always wins. And we can see that if we increase the number of time steps. So now, if I start with $100 and I spin the wheel 500 times, in all the 5 trials, I've lost money, lost quite a lot of money, about at least half my initial bankroll. So unsurprisingly, because the wheel is biased towards the house, eventually in the long run they will win regardless of how much money I started with. You might get lucky early on, you might profit for a bit, but in the long run almost surely you'll lose at this game, which is not surprising because it's a negative expectation game. So is there any way to beat the house at this game? Well, first let's look at some statistics. So by simulating the game hundreds of thousands of times, we can sort of estimate a probability distribution of what my final bankroll will look like after a session at the casino. So for here, we started with $100 as we did before, and we simulated 10,000 trials, each of those trials for 500 spins, and then we basically created this histogram of the data. So this histogram represents my bankroll after each round and the number of occurrences of that in 10,000 trials. So we can see, I believe there's a bucket at about 10 each. So in about 1,700 trials, I ended somewhere between $75 and $85. So, I mean, that's less than 100, so that's a loss. And you can see this thing's centered about 75, and sometimes I lose even more than that, and sometimes if I'm very lucky, I do profit. So for about, give or take maybe 500 of those 10,000 trials, the gambler got lucky and managed to leave with more money what they started with. Now, of course, this gets worse if you play for longer. So suppose we up the numbers to 2,000 spins, and we do 10,000 runs of 2,000 spins each. the results are even more grim. So about half the time the gambler goes bust and goes into the negatives, and they manage to make a profit at only about 1% of the total runs. So I guess the moral of the story here is don't play roulette. And if you really must play roulette, don't play it too often, because the more you play, the larger the chance it is that you'll go bankrupt, because it's a negative expectation game. So this agrees with what our intuition and what the math says. So is there a way around this? Well, some people reckon there's a strategy to beat roulette, and it's called the martingale betting strategy. So the idea is you bet $1 on each spin. Again, we'll say we're betting on red. And if you win, that's fine. You just keep doing the same thing. You keep wagering $1. If you lose, you then up your bet. You multiply your bet by 2. And after each consecutive loss, you basically double your bet to try and recoup your losses. So that way, when you eventually break a losing streak and get a win, you make all your losses back, and that way you can start making money again. I mean, surely this is a winning strategy, right? A surefire way to make free money. Well, it depends how much money you start with. The problem is that eventually, no matter how hard you try, there will be a streak of losses long enough to bankrupt anyone, no matter how much money you start with. So unless you happen to walk into the casino with infinitely many dollars, and if you have infinite dollars, what are you doing at a casino? Then this won't save you either. So we can see the simulations of this to help boost our intuition. So this is basically the same code as before, but I've modified it slightly. First off, I kill the simulation if the gambler goes bust, rather than allowing myself to go into the negatives. If the gambler wins a spin, they receive whatever wager that gets added to their bankroll, and the wager gets reset to $1. Otherwise, if they lose that spin, then we subtract off the wager, and then we double the staked wager. So whatever my current wager is, I double it up to wagering my entire bankroll. And so we'll have a look at the simulations of this, and it looks a little bit more promising than fixed betting. It sort of goes up and up and up for a bit. There's a few losses here that we recover from, but eventually there's a streak of losses so long it bankrupts the gambler and we're back to zero. And I mean, no matter how much money you start with, eventually if you play for long enough, you'll get a streak of losses so long that it'll bankrupt anyone. It's easy to sort of forget how fast doubling can grow, right? I mean, after only 10 losses in a row, you're already wagering $1,000 when you started on just a $1 bet. So suppose we upped the bankroll to $10,000, and again we start on just betting $1 per hand. You can sometimes get away with a profit. So you can see here we've simulated 5,000 spins, and in the purple trial, the gambler managed to get away with $2,000. I mean, that's quite good, right? But the problem is in that the other trials that happened did quite well, and then they had a streak of losses in a row, and then they went bust. So basically all we've done is we haven't changed the expectation value. It's still negative, but we've shifted the odds slightly. So it's very likely that you'll come away with a small profit, and it's very unlikely that you'll lose everything. But you compute the numbers out, you do the math, and it still comes out negative expectations. So sort of by analogy, it's like a 95% chance of winning $1 and a 5% chance of losing all of your assets. Would you take that wager? I wouldn't. So what's the moral of the story here? Martingale betting doesn't work either, and in fact there is no such betting strategy that will allow you to win on a negative expectation game like roulette. The maths doesn't lie. So that's enough on roulette. Let's move on to a different problem, numerical integration. So another application for Monte Carlo methods is for integration. As you may have seen before in calculus courses, we can approximate an integral sufficiently well by a Riemann sum. And so what's a Riemann sum? It's basically approximating the area under the curve, which is what an integral is, by a series of like little rectangles. And I mean, why do we care about integration? I mean, it comes up all the time in engineering. A lot of digital signals processing ends up being a lot of Fourier analysis, which is implemented as a series of integrals. So it's really important we be able to integrate things because it shows up all the time in different disciplines. So, I mean, for the moment here, I've just got a simple polynomial for the sake of example. But let's suppose, for whatever reason, we couldn't compute this exactly, and so I had to approximate it. So we can approximate the integral with a Riemann sum. So if I'm integrating over the interval 0 to 1, I'll break it up into little pieces. Each rectangle is going to be 1/10 wide. So we can approximate this integral by evaluating each point in my interval through my function, which in this case was squaring it. So it's going to be f of x, in this case f of x is x squared, times the width of the rectangle. And we bash that through, and that gives me 0.385, which is, I guess it's a sort of okay approximation to the true answer. I mean, we only got 1 decimal of precision here. But we can always do better. By using a finer partition, this provides to us a closer approximation. So here, I've used a partition of 1,000 pieces, and that gets me the approximation 0.338 and some change, which is 2 decimal digits of precision to the true answer, at the cost of extra computation. And so the idea is, however accurate you want the result to be, you can just choose a fine enough partition to get the result that you want. So why care about numerical integration? Why not just always use the exact answer? Well, there's a few reasons why that might not potentially be feasible. So first off, the antiderivative may not even exist. So for polynomials like x squared, well, we know how to integrate that. That's just x cubed on 3, right? But for any of these expressions, so e to the minus x squared, or sine x squared, or x to the x, these things don't have a nice, simple way to write down the antiderivative. There's no way to write it as like a finite combination of like powers and sums and logarithms or whatever. So we can't actually analytically integrate these things, which means we're basically forced to fall back on numerical techniques. Another reason why we might be forced to do this is the function that we're trying to integrate might not be a smooth function, but a collection of data. Rather than a closed formula. So for example, you might have some sensor that tells you your current velocity, say every 10 milliseconds, and it basically is collecting a log of all this data of all your velocities as a function of time. If you were to integrate that, that is find the area under the velocity curve, that will give you your position as a function of time, which might be something that you're interested in. So that would be another reason why they were forced to use numerical techniques. And the third reason is that the function, while it may be able to be integrated, it might be too difficult to do so. It might be like computationally expensive, or an approximation might be all that we need. If all we need is a number somewhere in the ballpark, it might be a lot faster to use numerical techniques, even if an exact solution can in principle be computed. So here's an example of some Python code to do numerical integration. So a Python code here is basically computing a Riemann integral of the function f on the interval ab, where samples here is going to be the number of rectangles in my Riemann sum. So total here is storing the area under the curve. We compute the step size, which is the width of the entire interval, which will be b minus a, divided by the number of rectangles, in this case divided by samples. And then what we do is we basically for loop for each sample, the x value, that is sort of this number here, corresponding to where the rectangle is going to be the left-hand side of the interval, which is a, plus I times the step times the number of rectangles so far. So that will tell me how many rectangles forward we're doing. We then compute f of x for that x, for whatever the function I'm trying to integrate is, and then we multiply it by the size of that step, and that will give me this rectangle here, the area of that rectangle. We then add that to the total, and then basically rinse and repeat. And of course, if the number of samples is higher, then we'll get more thinner rectangles, which will get me a closer approximation to the true answer. So that's all well and good, but this runs into a problem when we have a large number of dimensions to integrate over. So when we're integrating over just the real line, I mean, that's no worries, right? If the size of each partition or the size of each rectangle is epsilon wide, then we'd need, approximately 1 divided by epsilon many of slices to cover the entire interval. Now, consider the same problem, but in 2 dimensions. So imagine we've got our function is like a surface, and we're trying to integrate over a little patch, a little rectangle underneath that surface. We have to partition that grid, that is if we can't do it analytically, into little tiny grid squares, much like we take the interval and break it into little chunks, I'm taking my grid and breaking it into little tiny squares. Now the issue is if each square has side length epsilon, then I'm going to need 1 on epsilon squared many little tiles to cover this entire grid. And so suddenly this has gone from a linear time problem to a quadratic time problem. And in general, if the number of dimensions is very high, this gets a whole lot worse. In a d-dimensional space, you require n to the power of d many cells to get a comparable accuracy if you are integrating over just n many cells in one dimension. This problem is exponential in the dimension, which means even for like moderately large values of d, say 20 or 30 or so, this becomes wildly intractable. So this problem of this idea of the time taking to run blowing out exponentially with the dimension, that's called the curse of dimensionality. And so here's an example of sort of naive numerical integration in 2 dimensions. Basically, we're integrating over this region here, so it's like a patch where the width is from A to B and the height is from C to D. We basically have to compute a step size for x and a step size for y. So the step size for x will be b take a, which is the width of the rectangle, divided by the number of samples. Step size for y will be the height of the rectangle, d take c, divided by the number of samples. And then we have to double for loop over both width and height. We compute x, which would be the left-hand side of the rectangle plus however many steps in the x direction. We have to compute y, which would be the bottom of the rectangle plus however many steps in the y direction. We compute f of x, y for that x and that y. And then we multiply it by the size of the step in the x direction and the size of the step in the y direction. That's basically, instead of a rectangle, now you imagine it's a little square sort of extruded up this cuboid. So it's the same thing but in a higher dimension. And you can see how much more computationally inefficient this is going to be, because now with 2 dimensions we've got 2 nested for loops. And obviously this gets worse and worse as the dimension goes up. Every additional dimension is going to add another nested for loop. So for like 6 dimensions, 6 nested for loops, that's going to run terribly, right? Thankfully, there is a resolution to this problem, and the solution is quite surprising. Instead of chopping the domain into lots of uniform little chunks and sort of walking across and adding each chunk, you just randomly sample points uniformly from a bigger domain that you know how to sample from, and then you basically measure from the bigger domain how many points landed inside the region you're interested in, and then you approximate the integral as the number of points that landed inside the region D that you care about, divided by the number of points sampled in total. The advantages here is the running time is now totally independent of the dimensionality of the problem. It doesn't matter how many dimensions your problem is, the error can be approximated as 1 divided by the square root of n, where n is the number of samples. Where does the 1 over square root of n come from? It basically comes from a fact in statistics called the law of large numbers, where basically if you take an average, I mean, you can imagine if you have a circle inside a square, and I want to work out what proportion of the entire square's area is taken up by the circle. I randomly sample points. The proportion of the points that land in the circle relative to the total number of points will be proportional to the area of the circle. So by counting the number of points that land in the region that we care about, that gives me an estimate of its area, which is what an integral is. The downside here is that we need to be able to find a larger domain to sample from. Usually we just take a bounding box, but sometimes it can have its own problems that we'll get to in a moment. So we'll do an example here. The example I just mentioned, we want to estimate the area of a circle of radius 1. Of course, the area of a circle is pi r squared. R is 1. We're essentially estimating pi. So a circle is described by the relation x squared plus y squared is equal to 1. And we're going to sample points from the smallest box that circle fits in. So that is a box that's like 2 units wide and 2 units tall. And the circle sort of fits perfectly in that box. We sample points randomly from the box, and if the points satisfy the constraint x squared plus y squared is less than or equal to 1, that means they're less than distance 1 away from the origin, and so they'll be lying in the circle. So we have the code here to do that. We're going to take 1,000 samples, and then we for loop from 1 to 1,000. we randomly generate a point from x in the interval -1 to 1, and the same for y. We treat these two random numbers as like a random coordinate in 2D space, and then we check if the sum of the squares of those is less than 1, that means it's in the circle, and so we'll count that using the in-circle variable. And so here's sort of a picture of what's going on here. So I've got my box, and I've got a circle that fits perfectly inside, and then I just randomly sample points over this box. I count the number of points that landed inside the circle, divide that by the number of total points, and that'll be a rough estimate for the area of the circle. And as you add more and more and more points, this will get you a stronger and stronger approximation. In fact, we can see a plot of the error, and it matches the law of large numbers I was talking about earlier. So on the x-axis here, we have a logarithmic scale of the number of samples taken. And on the y-axis here, we have the relative error between my guess at the area of the circle, which is pi, minus the relative error of the true value of pi. And it almost perfectly fits the model of 1 over square root of n. So basically, whatever error you want, so if you want to be within 10 to the -3 of the true answer, that means you need to take 10 to the 6 or a million samples. And again, it doesn't matter if we were instead measuring the volume of a sphere in a box, or measuring the hypervolume of a hypersphere in a hyperbox, or however many dimensions you want, it will always satisfy this property. It will always go down as 1 over the square root of n, regardless of the dimensionality, which is quite a nice property. Now, of course, with any method, Monte Carlo methods have limitations. And so the first thing that will give us strife is when we have functions that have a domain of infinite size. So for example, like a bell curve, the bell curve is defined over the entire real line. And I can't exactly generate, I can't uniformly sample from an infinitely large domain, because between 0 and n, where n is a finite number, the likelihood that I get a number in that range relative to the entire real number line is precisely 0. So it can be quite difficult in general to sample from an infinitely sized domain. The sort of way you might solve this is you basically try to transform the entire real line to like a interval, and then you try to sample from that. So there can be more to try and fix it. Another problem is sometimes if you don't know a lot about your function to begin with, it can be quite hard to work out what domain you should choose to sample from. Because if you choose a domain that's too small and part of the function's poking out, then you'll get an inaccurate answer as to what the actual area is. So, and if you pick a domain that's too large, then most of the points won't land in the region you care about, and it will take a very, very long time to converge. This is the same problem you get is if you have a function that takes up very little room inside the sample domain. So suppose we did the same problem we did before, where we have the circle but inside a really, really big box, and I sampled, say, 1,000 points. If just by happenstance none of those points managed to land inside the circle, I'd estimate the integral as exactly 0, which is clearly absurd. And so the problem is if you have a function where the area that it bounds is sort of a very small fraction of the area you're sampling from, you'll have to sample millions and millions of points to get a reasonable estimate, because of those millions of points, maybe only 1 in 1,000 actually lands inside. So there are some mitigations for these problems. Importance sampling, where basically if you know something about the function, that is, you know the important parts, you can focus your sampling on there. So for example, for a bell curve, yes, it's defined over the entire real interval, but only the points near 0 actually matter, right? Most of the weight of the bell curve is pretty close to 0, whereas the tail end bits, they don't really matter that much. So importance sampling is you basically bias the sampling towards the parts that matter, and then you divide by a factor to account for that bias. That's one technique. Another technique is recursive stratified sampling, where basically, imagine we have the same circle and box problem as before. You basically chop this region up into a grid, and then you consider biasing the sampling towards different parts of the grid. So for example, there's a little grid square on the top left. All the points sampled there will lie outside the circle, and so that's not really interesting, right? We can focus less on that. If we're sampling from a grid cell entirely within the circle, Again, they're all going to be within the circle. That's not very interesting. The interesting ones are the ones that sort of lie on the boundary. So this sort of recursive stratified sampling technique basically focuses on the interesting parts. It focuses on the boundary between the inside and the outside of the curve automatically. I'm not going to get into the details of importance sampling and recursive stratified sampling. That's sort of a bit beyond the scope of what we want to do here. But you should sort of be aware that they exist. And most numerical integration libraries, like ones you call from Python or from SciPy, will automatically use a lot of these very clever techniques to speed up numerical integration. So that's enough about multi-color techniques. Let's talk about discrete event simulation. So often when we're trying to simulate something, the phenomenon that we're trying to simulate is going to be continuous in nature. And of course, our computers, being like discrete machines, don't deal well with continuity. So thankfully, we can sort of solve this problem by approximating smooth reality with like a discretization over a grid. So imagine we want to observe the diffusion of heat through like a bar of steel. Essentially, the function we're trying to approximate is a function that takes 4 numbers. It takes a point in space, which is defined by an x, y, z coordinate, and it takes a moment in time, defined by maybe number of seconds after we started the experiment t. It takes those 4 values, an x, y, z location and a time t, and returns to me the temperature at that location. And what we would like to know is, for say a particular point, how does the temperature of it change as a function of time? I would also like to know the temperature of the block as a whole for all the points inside the block. Now, of course, there's lots and lots of points inside a steel block. I mean, at the end of the day, this steel block isn't really continuous. It's made of atoms, but there's far too many atoms for us to simulate each one. So we cheat a little bit. We're going to discretize both space and time to achieve this in any sort of reasonable time frame. So to discretize space, we imagine taking the bar and chopping it up into little cubes, and we assume the temperature of all the points in the little cube is the same. So any point in one little cube is the same temperature as any other point in the little cube. So now this little cube is like one particular point in my discretization. This is not that unreasonable an assumption to make, because the temperature of the steel bar should be pretty continuous as a function of distance, right? There shouldn't be a point where it like suddenly jumps up in temperature very quickly, right? It should be like a nice smooth gradient. So by taking sufficiently short distances, that is, chopping up my steel bar into sufficiently tiny little cubes, this will be a pretty reasonable approximation for what the true value is going to be. We also need to discretize time as well by basically doing the same thing. We basically simulate the problem over a series of time slices. We have time slice 0, time slice 1, time slice 2, and we assume during a time slice, the temperature doesn't change, which again is a reasonable assumption, because if I have like a cup of hot coffee on my desk, over a period of a second, its temperature is going to be pretty constant, right? But over a period of like a minute or 10 minutes or an hour, its temperature is going to change a lot. So we can basically assume for sufficiently small time scales, the temperature is constant. That allows us to do this discretization trick. And the last thing we're going to assume is that temperature it's only a local change. So the temperature of one particle in the steel block can't affect a particle all the way at the other end. We're going to assume we can't do that. So when we're computing the update rule, we basically are only going to assume each cube, so each little part of the steel block, can only conduct heat to the blocks adjacent. Of course, in a more realistic model, you might consider the effects from like conducting heat via like radiation or by convection, but you know, we're making assumptions here to simplify the problem. We're basically assuming it's a steel bar in a vacuum, there's nothing else touching it. The only thing that matters is the temperature of the little parts of the steel bar. So for that reason, all of the assumptions we're going to make is that heat wants to move from hot cubes to cold cubes, and can only do that by moving heat to an adjacent cube. So we're going to assume we're just in 2 dimensions here, just to make the presentation easier and make the diagrams I'll show you easy to generate. We'll assume we've got a 2-dimensional grid, and the very top and the very bottom of the grid is going to be a heat source. So maybe that's connected to a flame or connected to the CPU of your computer, so it's basically pumping in heat. and we assume the left and the right hand side of the grid are heat sinks. So that's maybe like a literal heat sink or a fan or maybe water flowing past pulling heat out. So basically we've got this grid where heat's being pumped in the top and the bottom, and heat's being pulled out on the sides, and we want to see how the heat flows through this system. So we're going to make some assumptions, simplify things. We're going to assume after each time step, each cell will become a weighted average of its neighbours. And so what do I mean by that? I mean each cell on the grid is going to be some average of the 8 cells around it with a particular bias to some cells. The idea is the cells directly to my north and south and east and west are sort of closer to me than my diagonal neighbours, like my northeast neighbour and my northwest neighbour and so on. So we can have them affect the temperature more, we can give them a greater contribution, and this is something we can control with some parameter C. So what's going on here? So we'll run the simulation for duration many time steps. We for loop over all time steps t, and then we double for loop over all cells in the grid. We compute the average of the adjacent cells. So we basically take my current cell location at ij, compute the neighbours to the left, to the right, to the top and the bottom. We sum those up, and then we divide them by 4 to get the average. The next thing we do is we compute the average of my diagonal neighbours to the top right, top left, bottom right. We take the average of those, and then the new temperature of the cell will be some weighted average of the adjacent cells and the diagonal cells. So here, if I just chose C to be 1, this essentially degenerates down to the average of my 8 neighbours. But again, it seems a reasonable assumption to make that cells that are closer should conduct heat faster, and so the diagonal neighbours should affect the outcome less. And so we can sort of change how much that matters by tweaking the value of C. And so here, as I've said before, we'll sort of imagine the top and the bottom are sort of always hot, and the left and the right hand side are always cold, and heat can sort of propagate through the system. And here I've chosen C to be 2. So I'm going to assume that immediate neighbours matter twice as much, sort of conduct heat twice as fast as the diagonal neighbours. And so this is the initial configuration of the system. After 20 time steps, we can see the heat starting to propagate through. So the heat's moved to the cells, who move to their adjacent cells, and sort of so on. 40 time steps, 60 time steps, and then after 300 time steps, we can see the system beginning to converge to a steady state where the heat is sort of moving in from the top to the bottom and exiting out the sides. Eventually, after you run this for a long time, it's going to reach a steady state where each cell has just as much heat being pulled out as it has heat being pulled in, so its temperature will stay as a constant. And so this gives us a nice little model that's relatively simple to compute, but has some quite stark, interesting behavior. It allows us to basically simulate the heat flow of something in 2 dimensions. And you can imagine scaling up to 3 dimensions would be just as easy, right? You basically have a grid ijk, so you've got an x and a y and a z coordinate, and you basically do the same thing again. For each cell, you take the average of its adjacent neighbours, and then you can sort of propagate heat throughout a 3-dimensional solid object as a function of time. Thank you.